So a lot of this chapter we've been focused on simplifying roots or radicals and dealing with fractional exponents. So we're going to extend that a little bit today by applying those principles to solving equations and inequalities. Now, you can correctly solve a problem and not make any mistakes and get an answer that doesn't work in the original problem. That's referred to as an extraneous solution. So for the most part, we want to do the undoing principle like we normally do for solving problems. So you want to get the root on one side by itself. Then you got to undo that root by raising it to a power that undoes the root. And then if there's still a root left, which sometimes there will be, you got to just go back and repeat these. If there's not a root, then you're left with a problem without roots, and you should be able to solve it just like you normally would. But the last thing is you want to make sure you check your final answers. Sometimes they will work, sometimes they won't. If they don't work, they're referred to as extraneous solutions. So in a problem like this here, you want to first of all get the root on one side by itself. So you'd have to get rid of that minus 1. So add 1 to both sides. So the left side you just get the root, right side you would get 6. Now you want to undo that root. Well, we have a square root. To undo a square root, you want to square both sides. So if I square both sides, I get this on the left, and I get this on the right. So now we just get y by itself, 38. Then we'd want to go ahead and plug that number into the original problem to see if it works. Plug in 38 for my y, minus 2 inside of my root, minus 1, and I want to see what I get. I want to try to get 5 like I have on the right. Well, if I subtract this, I get the square root of 36. Square root of 36, you know, is 6 minus 1. That is 5. So since 5 is on the left and 5 is on the right, it does work. So that means your answer is 38. So here, you want to normally try to get the roots on one side all by themselves. However, we have two roots, and we can't get the root on one side by itself. But we do have one root that's on one side by itself, the bigger root. So we could just square both sides as it is. Now, on the left side, your square undoes your root. On the right side, your square does not apply to each one because we have this. Now, if it was the square root of, say, an a squared times a b squared, then that would just be ab. But if it's the square root of an a squared b squared, and either a plus or a minus, your root does not apply to each one when there's a plus or a minus in there. So then you got to think about, what does squaring mean? Well, squaring means just multiplying by itself. So left side, we're not going to do anything. On the right side, we have 2 terms times 2 terms, so we just have to FOIL 2 times 2. 2 times that negative root x, negative root x times the 2, and then your negative root x times your negative root x. Now we can go ahead and simplify this just a little bit. We have some like terms on the right hand side. So now we are still left with the root. So we'll go back and look at step 1, get the root on one side by itself. So I'd have to get rid of the 4, I'd have to get rid of the x. So I could subtract a 4 from both sides, I could subtract an x from both sides. If I do that, x minus x, that drops. Negative 12 minus 4 is negative 16. These x's drop, these 4's drop, leaving me with just negative 4 root x. Then I want to go ahead and get rid of that negative 4 in front of my root. So I'd want to go ahead and divide both sides by negative 4, and I just get this, which then I have my root on one side by itself, so I want to square both sides to get my final answer of x. So now I have x being 16. Now I need to check it. So I'm going to take a 16, plug it in up here for my x, plug it in over here for my x. So 16 for my x minus 12 inside of my root, and then 2 plus, plug in 16 there. So on the left side, I get square root of 4. Right side, I get 2 minus just a normal 4. Square root of 4 I know is 2. On the right side, I get negative 2. This is a false statement. 2 does not equal negative 2, so that means my 16 does not work. So I would just put down no solution. With that in mind, we're going to try a problem with a fractional exponent. Well, remember, a fractional exponent is a root. So you're going to try to get that root or fractional exponent by itself. So you want to add 3 to both sides. So now you have that fractional exponent, which is really a root. Now you have that root on one side by itself. You just have to undo that. If it's a cube root, you'd have to then cube both sides. Cube the right side is 27. Cube the left side undoes your root. Now it's just a nice normal problem to solve by subtracting 1 from each side and then dividing both sides by 2, and we get 13. Then you want to go ahead and check your answer. Take your 13, plug it into your original problem. Remember to check it. You always plug it into the original problem. So we're dealing with cube root because it's a 1/3 power. 2 times 13 plus 1 with a minus 3, and we want to see if we get 0. So 2 times 13 is 26, plus 1 is 27. The cube root of 27 is 3. But then this minus 3 here, 3 minus 3 is 0. That's what we're trying to get to. So yes, it does work because we got a true statement. So go ahead and try to do this one on your own and then watch the video to check it. So there's no way to get both roots on one side by themselves. So we just square it as it is. Square it as it is. Left side we have squaring of a single root, so that's going to cancel. The right side we have a subtraction sign in here, so that squaring does not apply to each, so you got to think about what does squaring mean. Parentheses times a parentheses. Left side doesn't change, so on the right side you FOIL, -1 times -1, do your outer terms, your inner terms, your last terms. Then you want to go ahead and try to get your roots by themselves. By the way, a root x plus a root x is 2 root x. You can get rid of this x by subtracting an x from both sides. Get rid of this 1 by subtracting a 1 from both sides. And then we would get a 4 is equal to our 2 root x. Get rid of that 2 by dividing by 2. Then you have your root on one side by itself. Then you want to undo your roots. So to undo your square root, you square both sides, so we get x to be 4. Then you want to go ahead and check it to see if it works. Plug a 4 into your original problem for each one of your x's. So we'd have a 4 plus 5 in front of that root. We'd have a -1 minus the square root of our 4. Here we get the square root of 9 on the left. Over here we get -1 minus a 2. So on the right we get -3. On the left we just get +3. Not true, so it's a false statement, so no solution. So now we're going to take a look at solving an inequality that has a root in it. The first part is very similar to what we were just doing. You want to get the root by itself, so you'd want to subtract a 4 from both sides. And then you'd want to square both sides to undo your square root. Square the left side just leaves you with what's inside of your root. You square your right side, you get 9, and then you want to solve it like normal. So add 6 to both sides, divide by 5. However, you need to remember that what is inside of your root can't be negative. So this can't be negative. So what's inside of your root, this can't be negative, means it has to be greater than or equal to 0. So now we have to solve that. So we could add 6 to both sides, divide by 3, and we get this. So we need both of these answers to occur at the same time. Technically, there's an AND statement between these, because we need this over here and what's inside of your root to be positive. So, whoops, we need both of these. So we're going to graph that. Now that's your final graph, but to help you understand it, when we are looking at this part here, it's really a closed-in circle here, shading all the way to the left. Looking at the other one, this one here, it's really a closed circle here, shading all the way to the right. And when you are dealing with an and statement, you need both of them to be true. Well, they both only work where it's shaded in between. So that's why our final answer down here in the number line is only shading between 2 and 5, and including 2 and 5 because of the equal to here. If there was no equal to up here, then there would be an open circle at our 5. Now, if you're shading in between two numbers, you can write that as a compound inequality with your variable in between your two numbers.